Hello everyone, I'm Wei Sun. Today I will present our work, DeepRange, acoustic ranging via deep learning. This is a joint work with Wenguang, Wang, and Lili from UT Austin. Ranging performs a critical role in human-computer interaction. Many applications are based on the capability of accurate ranging. For example, VR and AR devices use ranging to detect hand movement. Smart speaker and car can detect users' hand gesture with ranging. We focus on the acoustic ranging on mobile devices. It is increasingly popular in recent years because it has unique advantages compared to other methods. A pair of speaker and microphone are equipped on most devices. The speaker can send out the signal and the microphone can detect the reflection to measure the time of flight. Besides, it consumes less power considering the low signal rate. It is critical to mobile devices. Acoustic has a centimeter level wavelength so that it can achieve better resolution than Bluetooth and Wi-Fi. Finally, acoustic has a broad effective range. It is a good fit for indoor applications. There have been many signal processing ranging by analyzing source signal and reflection signal. Beep Beep and Finger IO try to measure the time of flight by computing the correlation. LLAP and Strata manage to detect phase change. CAT and RTrack prefers to use FMCR-based method. It transforms time delay to frequency offset. We propose an interesting and fundamental question for ranging problem. Can DNN learn ranging purely based on raw data? We want to input raw samples of FMCR signal and output the range estimation. We have several intuitions for this proposal. First, DNN can approximate any function in theory. Practically, DNN has a huge potential to achieve higher accuracy. It has been proved that DNN improves the performance a lot in computer vision tasks. We can learn from DNN structure to design the diagram of our signal processing algorithm. There have been some work using deep learning to improve the accuracy. Our goal is to explore if it is possible for DNN to learn ranging purely based on raw samples, and if it can outperform the existing processing. To enable data-driven approach, first, we need a large volume of high-quality data. However, there is no open dataset for this task. It requires to take much effort to collect the data, considering the diversity of environments, mobile phones, different positions of target reflectors, and interference reflectors. If the data is not sufficient and diverse, the model can be easily overfitting and lose the generality. Thus, we propose to use realistic simulation to generate a huge amount of training and validation data. First, we consider the white noise with different energy bar. Then, we take account of multipath interference caused by nearby reflections. We cannot neglect the direct path signal comes from mobile phone speaker to the microphone, which is the self-interference. Even though we perform the background cancellation, we still add the residual self-interference due to the imperfect cancellation. Finally, frequency response is also critical for simulation. It represents an uneven response gain to different frequencies. As the figure shows, the standard FMCW will have different magnitude at different frequencies. We use the random spin to represent the frequency response. We need to design an appropriate neural network structure to learn the hidden pattern from the simulation data. The chirp time series signal is long and does not have a clear local pattern. Finally, we develop a long filter-based CNN to capture the signal features. We start from full connected neural network, which has achieved a promising accuracy. We figure out that the first layer of FNN has strong correlation to FMCW signal. It motivates us to use a convolutional neural network, which uses a diverse kernels to capture different local correlations. We use a small kernel from 3 to 11. We find that larger kernel is better and keeps increasing the kernel size. Finally, we use a kernel size of 1440 with 4 channels, which is the DRNet. We have trained DRNet and evaluate performance on real traits. We collect more than 160,000 test samples with 11 different smartphones in different environments. We detect various targets, including 10 users' hands. We add interference by adding other objects around the target. We evaluate our model on the different SNR and compare with other methods. When the SNR is high, all the methods can achieve a low distance error. However, DRNet is more robust to the worst SNR. It reduced the median error by a factor of 3 in the worst case. We performed thorough ablation study on the model. We visualized the CNN kernel of 4 channels. We found that 3 channels show similar time frequency property to a standard FMCW. However, they have an uneven energy distribution. One channel distributes small energy detection pattern, especially at the head and the tail of the sequence. It implies that CNN kernel not only perform trivial FMCW correlate detection, but also show the diversity to detect uneven pattern, which can combat the noise and interference well. In conclusion, we have such contributions. A realistic acoustic simulator for ranging to easily generate large amounts of training data. The DRNet that takes those acoustic samples to output a range. We also provide insights from the DRNet ablation study. Thank you.